This lecture, we're going to talk a little bit about Newton's first law. And my guess is by this point in your physics careers, you've all seen a little bit of Newton's laws at the very least. But let's go over it once to be sure. Newton's first law says an object in motion will remain in motion, and an object in rest will remain at rest unless acted upon by an external force. Now, I know that's a lot of text to take in at one time. What does all of this mean together? So let's take this a little bit at a time. Let's start with the first part. An object in motion will tend to remain in motion. Now, this is the part that seems obviously false. If you throw a ball up in the air, not only is it not going to stay in motion, the direction of motion is going to change. Eventually, it's going to hit the ground. It's going to stop. And this held back the field of physics for a long, long time. And now we're going to go into something a little bit non-technical. This isn't the hard numbers physics you'd really expect, but this is an important piece of historical context. For the longest time, starting with Aristotle and going up pretty much through Galileo, people believed that objects wanted to be in motion or wanted to be at rest. So for instance, if you're a farmer and you're trying to plow a field, you have your field, which is, bumpy and rocky. There's a big rock in it. And you notice that when you push on the rock, you apply a force to it, it starts moving, starts rolling end over end, and then it stops, just sticks in the ground and doesn't move. So what you conclude from this is, the rock doesn't like to move. Its natural state is resting. Now, maybe you notice there's an apple tree. Really poorly drawn apple tree, I know, but bear with me. And you notice the apples tend to fall off. And you say, well, the apple's in the air. They want to move. Their natural state's moving. Now, all of this is entirely wrong. There's no natural state. It's not like the apple can be happy in one state and sad in another state. Instead, what we're saying is there are forces. And in the absence of all forces, an object in motion is going to tend to keep moving. So what's an example of that? If you've ever watched the sport of curling, which involves sliding big rocks along ice, you have a big sheet of ice. Now, ice isn't quite frictionless. There's some friction, which is a force, that'll slow things down. But it's pretty negligible, so we can ignore it for now. And in this sport, you slide these big rocks, and you start them moving, and they keep moving. And they don't change or move, or change directions, or reflect or anything until they hit another rock, or the wall, or some other obstruction. And why is this? Well, there's no outside forces. So this brings us to the last part of the law, and we'll get to the middle part in just a second. The last part of the law says, unless acted upon by an external force. And what this means is there's an extra force. Gravity is one such force. That's why the apple falls even though it's stationary. Another force would be friction. That's why the stone stops moving even though it has motion. All of those things, friction, gravity, etc., are external forces. And this is one of the most critically important parts of Newton's laws. You have to interpret them exactly as they are. They are one of the most powerful tools when it comes to physics. They're incredibly precise and incredibly general. But the thing is, you have to interpret them exactly the way they're written. It's very, very tempting to use them in ways that they weren't meant to be used, and to feel like you're obeying the law, but you aren't actually. For instance, let's take an obvious example. We have the Earth and a little satellite going around the Earth. So our satellite's flying around. And we can think of our satellite as an object in motion, staying in motion, right? It has some velocity. It's moving around the Earth. It keeps going, doesn't slow down. There's no friction in space. There's no external forces, right? Makes sense. Except, no, that's not true. What external force are we seeing here? Well, it's not moving in a straight line. And that's really what Newton's law is saying. The velocity can't change. So the fact that the velocity is changing, it's going in this direction over here, and in this direction over here. And as I'm sure you remember, velocity is a vector component. Direction matters. So there is some force because velocity is changing. And we call that force gravity. A lot of times we write gravity, F sub g. So you should know that for future lectures. So even though the satellite seems like it's the perfect example of objects in motion staying in motion, it's a terrible example. Why? Because there's an external force, which entirely invalidates Newton's first law. Now you can find ways around that. Let's say we have a spaceship far, far away from anything in the universe. It could be flying along, and maybe it is so far away from stuff that gravity is negligible, we can ignore it. Then it's just going to move in a straight line, unbothered by gravity, friction, etc. It's obeying Newton's first law. But the thing is, as soon as you introduce any kind of friction, gravity, any external force into the system, you have to stop using Newton's first law. Now, is there a mathematical way we can think of Newton's first law? And as it turns out, there is. What we can say is that acceleration equals 0 if and only if, so the if with two F's means if and only if, acceleration equals 0 if and only if net force also equals 0. So what does this mean? This means velocity doesn't change, because acceleration's change in velocity. And since acceleration doesn't change, there's no acceleration, velocity doesn't change, then an object in motion will stay in motion, a positive velocity will stay positive, and an object at rest will stay at rest. If velocity is 0, and there's no external force, net force equals 0, then acceleration 0, so velocity stays 0. So based on this, you can start to see some of the powerful conclusions we can draw based on Newton's first law, but you can also see from some of our examples how it's very easy to be tricked by Newton's first law, and how very important it is that you focus and make sure there are no external forces when you're applying this law. Now, you can solve physics problems where there are external forces. It's one of the big things you do in physics, but that's going to need more of Newton's laws.